2 females, you're picking out of 6 women. So you multiply those, that turns out to be a probability of 1/2. Finally, you get to, excuse me, X is equal to 3, all 3 females. You could have done the actual probability as we've done for the first 3 of them, or because we know that the sum of all the possibility, all the probabilities for all the outcomes must be equal to 1, we could just say 1 minus these other 3 probabilities, we turn out to have 1/6. So these probabilities that we've worked out, probability X equal to 0, probability X equal 1, probability X equal 2, probability X equals 3, this describes the probability distribution for this particular random variable of interest. So that is just a brief look, and we're going to be working a lot with examples, particularly when we get to meeting up with each other in the class, going through some exercises that really kind of hone your skills and work with a lot of different distributions. Cumulative distribution function. F of B for a random variable X is the probability that X is less than or equal to B. Okay, so we could have said, what's the probability in the previous example, if I were to give you the cumulative distribution function, what's the probability that F of B, so F of 3 would have been the probability that the random variable is less than or equal to 3, well, that's going to be equal to 1 because you're adding up all those. What's the probability that X is less than or equal to 2? That's the capital F of B, the cumulative distribution value for 2. So what's the probability that random variable X is less than or equal to 2? You're going to add 1/30 plus 3/10 plus 1/2. F of 1, probability that X is less than or equal to 1, that there's at most 1 female in the final 3, is another way to say that. That would be found by adding probability X is equal to 0 plus the probability that X is equal to 1. You would therefore add 1/30 plus 3/10. So that is, you're putting some numbers to what this kind of mathematical definition is. F of B, probability that X is less than or equal to some value. And just as I did in what I was just saying, F of B is equal to the summation of all the probabilities up to the value B. F of 1 was the probability of 0 plus probability of X equal 1. Probability F of 2 was the probability adding up the 3 probabilities. X is equal to 0, probability X is equal to 1, probability X is equal to 2. You add up those 3. So that's all that's doing with the summation sign. As an example, here we go. Recall the example, X denotes the number of relays that closed properly, has a probability distribution function given by neither of the relays working, had a probability of 0.04, probability that one of the relays was working, 0.32, and the probability that both relays were working, i.e. X is equal to 2, had a probability of 0.64. Cumulative distribution function for this random variable then has the form probability that X is less than or equal to 0 is of course 0. Probability that X is the random variable takes a value less than or equal to, or rather strictly less than 0 or less than 1 would be just the probability of 0. Probability that the random variable takes a value between 1 and 2. Actually, this is a typo. That should say, sorry, let's go back here. Sorry, there is a typo on that slide. You're going to want to add up for all values between 0 and the value B. So this should actually say between 0. So on the third one with the double question mark should say B between 0 and but less than 2. Then you'd be adding up 0.04 plus 0.32. Probability that the random variable X takes a value that is less than or equal to 2 would be just the sum of all three of those, which is 1. Okay, so that gives you a sense of what's the probability distribution. Brief glance, and again, we're going to go through examples on this in the general definition. What is a cumulative distribution function look like? And next we look at what is something called expected value of the discrete random variable x with probability distribution p of x, little p of x. And that is something that's given by, and we call this is mu, that the Greek symbol. Another way to say that is say the E of capital X, so the expected value of X is equal to the different values that the random variable could take across the whole sample space, all the different outcomes, times, so the values that it takes, the random variable can take, times the probability of X. And you sum that up, that product up across all X, the different values that the random variable can take. And what is the interpretation of mu? It's an average of the random variable in the long term. So let's go through an example of this. Suppose you and a friend are matching balanced coins. Each of you tosses a coin. If the upper faces match, you win $1. If they do not match, you lose $1. Your friend wins $1. The probability of a match is 0.5, and in the long run, you should win about half the time. On average, how much will you win over the long run? So, probability of 0.5 that they match, therefore, probability of 0.5 that they don't match. If they match, you win $1. So you want to say 0.5 times $1 plus 0.5 times minus $1, because you'd have to then give $1 to your friend. And so the expected value in this case is 0. You'd end up with a 0.5 plus a negative 0.5, which zeroes out. So that's called a fair game then. That would be your expected value. Okay, so now the next one, learning checkpoint. This is something to work out on your own. I'll kind of talk you through it as well, since that previous example wasn't that strong. The manager of a stockroom in a factory knows from his study of records that the daily demand, the number of times used for a certain tool, has the following probability distribution. So if there's a 0.1 probability that the demand, nobody asks for it, the demand is 0. 0.5 probability that there is one request, one demand for the certain tool, and 0.4 probability that it is requested twice during the day, whatever the day defines. In other words, 50% of the daily records show that the tool was used one time during a day. Okay, and what this in the parentheses implies is that, again, part of the hard thing of this is, well, how do you derive a probability? You could say that, well, maybe there's a company that's been in existence for 10 years, and they recorded all the daily data over those all 10 years, and then they went back and looked at all this historical data and identified that 50% of those days the tool was requested only one time. 40% of those days of the data that was collected, the tool was requested twice during the day. Letting X denote the daily demand, find the average number of times the tool is used, or E of X. What's the expected value of X? What's the expected number of times the tool is requested during a day? Okay, so that turns out to be, and I'll go ahead and tell you this, back to our what is E of X. Okay, we're going to take the value that the random variable can take times the probability that it takes that value. Okay, and you're going to add that up for each of those. So, the value the random variable can take, 0, times the probability that it takes that value, 0.1. So add that to the value that it can take, 1, times the probability that it'll take that value, 0.5, plus 2 times 0.4. So you add those three up, 0 times 0.1, 1 times 0.5, 2 times 0.4. And that's how you get the expected value. Expected number of times, the average number of times the tool would be requested in a day. Okay, so the next thing we look at from there would be expected values of functions of random variables. If x is a discrete random variable with probability distribution p of x, and if g of x is any real valued function of x, then the expected value of g of x is equal, now this is just extending it, instead of having x here, we have g of x times the probability that that the random variable takes a specific value x. And you add those all up. Okay, so this is a bit of an extension of the expected value as we just were looking at it. It's an expected value of a function of the random variable x. So suppose you and your friend up the stakes to $10 per game of matching coins. You lose $10 or you win $10 with equal probability, 0.5. Your expected winnings for the game, so this is where instead of having x here, the $1, we have a g of x, which is 10 times 1. So we had a half of the probability, 0.5 probability that we would lose. So that's the g of x is minus 10. And then the probability of winning is a half. And now instead of seeing a $1 here, we have 10. So it's still a fair game. But note that, if x represents your winnings per game when you were playing for $1, then 10x, the g of x here, represents your winning when you're playing for a $10 game. Okay, recall the manager at the stockroom in a factory knows from his study of records the daily demand number of times used for a certain tool follows this probability distribution. Just what we had a moment ago. Now, again, this is taking the same one on the previous slide. Imagine that g of x is the function 10 times each time the factory uses the tool. How much should the factory budget per day to cover the cost of the tool if they use the average daily cost? So instead of having x, you have 10x, right? So 10 times 0 times 0.1 plus 10 times 1 times 0.5 plus 2 times 10 times 0.4. That would give you the average budget per day associated with the factory using the tool. And I'll let you write those numbers down. Just, check that out by yourself. But that instead, so that's where, it gives you a flavor of where the function is important, the g of x, and using some of these relationships. Okay, so that's the expected value gives the long-term average of your random variable. Now we look at something about the variance associated with a random variable x with an expected value mu is given by something called variance. And you'll see this sigma squared. You're going to live and breathe and get familiar with this quite extensively here in the next sections, as well as the expected value mu. So what you're doing is basically saying, okay, let me look at the values, the different values that the random variable can take. We've got that denoted here with little x, minus mu, and then square those differences. Okay, and then multiply it, weight it down in a sense, and then multiply it by the probability p of x. Okay, and you sum up all those values over all the possible values of little x that your random variable x can take. And that is what's called the variance associated with a random variable. And so this is two different ways. You can go through and do this easily in Excel. We're certainly, again, going to work through some exercises to make sure you get this point. And there's two different working formulas you can plug in, x minus mu squared times p of x, or you can use this other one, which is the sum of the x squared times the probability of x, and then add all that up, and then separately then subtract off mu